Hello and welcome to Empowered Learning. This video will be about examples of basic matrix operations. And so some of the things that we'll talk about in this video are the placements of elements in matrices, as well as how to add and subtract matrices, how to multiply matrices, and in particular, learning that matrix addition is commutative, but matrix multiplication is not commutative. And of course, we'll see various other types of examples as well. So let's go ahead and get started here. So the first thing I have drawn to the right is a basic matrix. And so what a matrix is just an array. And so we normally use matrices whenever we have a group of a large system of equations and we want to be able to manage them, to be able to work on them simultaneously. And so that's one of the ways that matrices are used. Whether you realize it or not, for all of you that have nice flat screen TVs, what you're actually looking at is a big matrix. And so the number of pixels, both in its length and width there, sort of relates to the resolution of the flat screen TV. But really all that's happening there is that in each of those pixels, you have a particular color that's being shown there for each fraction of a second. And so based upon what that color is, there's a certain code that goes there that says that, hey, you should show black in this pixel, or you should show red in that one, or you should show green in that one. And so of course, for every fraction of a second that a scene changes in a particular TV show or whatever it is that we're watching, we see that all that stuff is changing. It's just a bunch of matrix multiplication going on. So my point is that matrices are used a lot more than what we may realize. So in this particular example, very first problem that we have is asking us to complete this sentence, which says the notation A35 refers to the entry in blank row and blank column of the matrix. So to learn about the anatomy of a matrix here, the first thing that we need to know is that matrices are characterized by its size or its dimensions. And so for its dimensions, it is described as row by column, where the row is the M in this case and the column is the N. And so for this particular element that is within the matrix, that's telling us that this element is at the location of, it is in row 3 and column 5. Okay, so we're going to say in the 3rd row and in the 5th column. Okay, so we see that we got that correct. And so if you see how they do here in my math lab, they name everything in terms of I and J instead of M and N. So as long as you know that the first subscript always describes the row and the second one describes the column, it doesn't matter what notation you use there. So moving on to the next question. All right, so the next question that we're asked is, what is the order of a matrix with 2 columns and 3 rows? And so the order of the matrix is just what its size is. And so how we're going to look at that is, again, row by column. And so order is another way of saying dimension here. So if we have something with 2 columns, then that means in this case, our N is going to be 2. And with 3 rows, that means our M is going to be 3. And of course, we go M by N. So that should be a 3 by 2 matrix. Okay. So our next question says a matrix that has the same number of rows and columns is called a certain type of matrix. And so for here, we know that those are called square matrices. And so I'll go ahead and give you an example of why here. I'll go ahead and erase all of this. Let's get rid of all this. All right, so in this case, what I have drawn here is actually a 3 by 3 matrix. And so we see here that the rows and the columns are the same. And you see how this would look like a square. So if we kind of put a box around this, we would say that that looks like a square because the dimensions of the row and the columns are equal to one another. Now, the important thing to know about square matrices is that square matrices are special in that if we were actually going to study this, square matrices are the only types of matrices within the matrix world, as I like to call it, that actually have inverses. Okay, and so where that comes into play is let's say we have an equation that's going to be like this. So let's say a times x equals b, where a and b are coefficient. Well, let's say a is a coefficient matrix, B is what's called an answer matrix, and X is our variable matrix. So to kind of give you an example of what that looks like, I'm going to make up a system here so you can see how that inverse part is important. All right, so here's an example of what a 3 by 3 matrix system equation would look like. And so for this, if we wanted to just solve for what our variable x was, and in this case it's the column matrix x, what we would need to do here is actually be able to get rid of this matrix A by basically multiplying by, in matrix terms, its reciprocal, okay? Multiplicative inverse, okay? Now, of course, with matrices, it's a little different than just dealing with the normal numbers and normal equations that we're used to, but the concept is still the same. If I want to get rid of this, I would have to do the inverse of this to be able to do it. And if I do it on one side, then I would have to do it on the other. And so I would have to come in here and actually stick in A inverse times B there. And so that's my point in one of the reasons why square matrices are important, because they're the only ones where we're able to solve these types of equations here. And we actually use matrices to solve systems of linear equations. And of course, one of the rules is for systems of linear equations is that you have to have the same amount of equations as you do unknowns. Okay? And by that rule, what that's implying in this case is that if we're going to model that system of equations in matrix form, then we have to have the coefficient matrix be a square matrix, be a square matrix, I should say. Okay? So let's go ahead and move on to the next question. All right, so now we're loading up question 4. And so what we want to do now is fill in the blank so that the resulting statement is true. Sorry. So what this question is trying to exercise is, do you know the equality properties of matrices? And so simply put, if we have some matrix A, B, C, D, and it's equal to another matrix E, F, G, H, then that means the elements that are in the same spots must be equal to one another. So in this case, A will equal E, B will equal F, C will equal G, and D will equal H. Okay? So using that over here, we know that X is what's missing here, but of course, that's going to be -9 over here, so X would have to be -9. Okay. Also, we see that Y over here, we don't know what that is, but over in this matrix, we see that is 6. So Y would have to be equal to 6. So X would be a -9 and Y would be 6. All right, let's move on to the next question. So for this question, we want to know if the following statement is true or false. And so we want to know, can matrices of different order be added? Okay, so let's look at this for a second. So let's say we had a matrix here, let's say 1, 2, 3, 4, and we wanted to add it to another matrix that is 4, 5, 6, 7. Whenever we do matrix addition or matrix subtraction, then we have to, in order to be able to do that, we have to have the same number of elements in the same places for each matrix. Okay, so this is a 2 by 2, and this is a 2 by 2. And if we added these together, we would say 1 plus 4 is 5, and 2 plus 5 is 7, and 3 plus 6 is 9, and 4 plus 7 is equal to 11. Okay, so in that instance, we see that that works whenever we have square matrices or matrices of the same order. Okay, now I could also add another row to this. So let's say I had a 0 here and a 2 there, and let's say I had a 1 there and a 5 there. Then of course I would be adding some more stuff here. Well, 0 plus 1 is 1, and 2 plus 5 is 7. And so in that instance, we see that we have now, let's erase that, we have a 2 row by 3 column matrix for each of these. So it doesn't necessarily have to be square, it just has to be of the same order. If we tried to add something else that did not have the same order, we wouldn't have everything to match it up with. And so I'll give you an example of that here. So let's say we come here and now we have an extra row here, 0, 5, 8. So we come like this. So, and we're trying to add this now to a 2 by 3. So this is a 3 by 3. And of course, there's nothing for 0, 5, and 8 to add up with over here. So that's why we cannot add matrices that are not of the same order. Okay. So this would be false as a result. All right, moving on to the next question. So this question says, if A is a M by N matrix and B is an N by P matrix, then when we multiply matrix AB, it is defined as a, and then we have to pick the dimensions of that matrix. And to find the product of AB, the number of, in this case, either rows or columns in matrix A must equal the number of rows or columns in matrix B. So I'll explain about matrix multiplication, what we have to have, and explain to you why matrix multiplication is not commutative. And from that point, you'll see how to answer this particular question here. So I'm going to clear out some room over here to the right, and we'll get to this in just a second. All right, so the first thing we need to know about matrix multiplication is that matrix multiplication is not commutative, meaning that, and I'll just put this in simple real number terms, in the world of matrices, 2 times 3 is not necessarily the same thing as 3 times 2, okay? So if we look at this, let's say we have some matrix XY. It is not guaranteed that matrix X times matrix Y will be the same thing as matrix Y times matrix X. Okay, so because of that, it depends upon the order in which the matrices are multiplied. Okay, now other than that, the other thing that we need to know is whenever we are multiplying matrices, the inner dimensions of the matrices have to match. And so to make my point there, I'm going to take this simple matrix A and matrix B and multiply them together. So if I said matrix A times matrix B, then do you see here that I have a 2 by 2 matrix being multiplied by another 2 by 2? And so as long as these two inner dimensions, as I'm calling them, as long as they match, then we know that we can have a result. Now the resulting matrix will be whatever the outside dimensions are. And so here we know that the result of this would also be, in this case, be a 2 by 2 matrix. Okay. Now let's say if I wanted to multiply A and C together. Okay. If I multiplied A and C together here, and let me get rid of these equal signs because that's not really what I'm doing here. So if I multiply A and C, notice that A still is a 2 by 2, but now C is a 2 by 3. And so the inner dimensions still match. So that means here my result is going to be a 2 by 3 matrix whenever I multiply. Okay. Now let's switch this around and say now I want to multiply C times A. So now if I do that, I have a 2 by 3 matrix, and then I have a 2 by 2 matrix. The inner dimensions here don't match, so here I can't multiply this together. So by definition, for matrices, that is undefined. And so here you see what has to be the same is we know that the second number represents the columns. So the number of columns here has to be the same as the number of rows. So when we go back to this question here, it says if A is an M by N matrix and B is an N by P matrix, do you see how the columns for matrix A matches the rows for matrix B? Okay. And of course the result would be an M by P matrix there. So to find the product, the number of columns in matrix A has to equal the number of rows in matrix B. Okay. And so we'll go ahead and go on to the next question. All right, and so I've been repeating this several times. We know that matrix multiplication is not commutative. Okay, and I'm going to actually display that here in this next example. So I'm going to erase some of this, and then I'm going to multiply A times C and then C times A to show you that we get different things whenever we do that. All right, so we're actually going to multiply matrix A and B together and B and A together versus A and C. So I think that'll be a better example. So if we look here, how we actually multiply matrices is we multiply each element of each row with this corresponding element in the column of the other matrix. So here we'll be taking 1 and multiplying that times 0, which is 0, plus we'll take 2 and multiply that by 1 here, which is 2. And so that result for this row and that column is going to be 2. Okay? And so we repeat that process. Oops. Yes, we repeat that process for the rest of these elements here. So we've done row 1, column 1. Now we're going to do row 1, column 2. So we're going to say, in this case, we have 1 times 5, which is 5, plus 2 times 1, which is going to be 2. Oh, yeah, and I see I did that wrong. So let me come back here. So I didn't do first part wrong. Well, I did the second part right, but the first part wrong. So let me go back and do that again. So here for the first one, this will be 1 times 0, which is 0, and then that'll be plus 2 times 2, which is 4. And so 4 belongs there. So sorry about that. And so now for the next space here, we say 1 times 5, which is 5, plus 2 times 1, which is 2, and that ends up being 7. So next we come down here for row 2, and we multiply it with column 1, and then row 2 multiply it with column 2. So 3 times 0 is 0, plus 3 times 2 is 6. So that result there is 6. Similarly, if we say 3 times 5, that gives us 15, plus -1 times 1 gives us a -1 there, and that gives us a positive 14 as a result. So whenever we multiply matrix A times matrix B in that order, that's what we get as a result there. So now what I'm going to do is erase this and show you how we end up getting B times A, which we'll see that when we do that, it won't come out to be the exact same thing as A times B. And the only way that it will come out to be the same exact thing is if those two matrices are what we call inverses of one another. Okay. All right, so let's come down here and multiply these two together now. So for here, we'll do the same thing. We'll say multiply row 1 with column 1, which is 0 times 1 is 0, plus 5 times 3, which is 15. So that first space would be 15. And you already see we have this being different there. We continue on and say row 1, column 2. So 0 times 2 is 0, plus 5 times a -1 is a -5. So we have a -5 right there. Going down to row 2 for B, row 2 times column 1, row 2 times column 2. So 2 times 1 is 2, plus 1 times 3 is 3. And of course, that's going to give me 5 there. Okay. And here, we'll say for row 2, column 2, 2 times 2 is 4. And 1 times a -1 is a -1. So that gives us 3. And as you see, although these two are both 2 by 2 matrices, A times B is not the same as B times A. So let's go ahead and move on to the next question. All right, so for here, we want to give the order of the matrix, in other words, its dimensions, and then after that, we want to identify what elements are in the locations of A32 and A23. So for this one, we know that we have 1, 2, 3 rows and 1, 2, 3, 4 columns. So this is going to be a 3 by 4 matrix. Next thing, this element in the location of A32 means in row 3, column 2. So row 3, column 2. That is 1/5. And then, of course, A23, which is row 2, column 3. See, 1, 2 row, column 1, 2, 3. That is a -2. All right, let's move on to the next question. So now what we want to do is find the variables x, y, and z such that this matrix equation is equal. All right, so let's first write down this again, but we're going to write this down knowing what the relationships are. So if you remember, for each matrix, whatever element is in, let's say, spot A11 has to be equal to the element that is in spot 11 here. So here we see that from what we are looking at with these two matrices, that X will have to be equal to 12. We also see that 2Y is going to have to equal 2. We see that Z will have to equal 17. And of course, 18 equals 18. So we already know that. So here we know that our X is 12. And from 2Y equaling 2, we know Y is going to equal 1. So we got an answer for X, we got an answer for Y, and of course we got an answer for Z. So we'll just go ahead and enter in that information. So X, Y, and Z. All right, so let's move on to the next question. So now what we want to do is take these two matrices, A and B, and we want to add them, we want to subtract them, and we want to multiply them, as well as multiply by a constant and then add them together. All right, so we have our two matrices written down, and so the first thing that we want to do is do the sum of these two matrices. And if we do the sum, then we know that the elements that are in each of the respective spaces, we have to put them together here. So we'll have 6 minus 6 for this first one. We'll have 6 plus 9 for the second one. 1, negative 1 plus 9 here. 4 plus 3 there. 7 minus 9 there. And 8 plus 3 there. And of course, we just get the results. So that's 0, 15, 8, 7, negative 2, and 11. So that's what A plus B will be. Now, of course, A minus B will just be, we're doing subtraction now. So here we'll have 6 minus a negative 6 for the A11 spot. And then we'll have 6 minus 9 for the second spot on the first row there. For the second row, we'll have negative 1 minus 9. Next, we'll have 4 minus 3. And then 7 minus a negative 9. And then 8 minus 3. And you see there, minus a negative is the same as addition. So that will give us 12. 6 minus 9 is negative 3. Negative 1 minus 9 is a negative 10. 4 minus 3 is 1. And 7 minus a negative 9 is the same as 7 plus 9, which is 16. And 8 minus 3 is 5. So we see that that is what the difference is. Now, if we say 5 times A, then of course all that's going on there is we're multiplying each of our elements in matrix A by 5. So which makes it pretty simple to do. So that's 5 times 6 is 30. So 30 once and 30 twice. 5 times negative 1 is a negative 5. 5 times 4 is 20. 5 times 7 is 35. 5 times 8 is 40. So that is what 5 times 8 is. So we'll go ahead and enter these in, and then we'll make some room to do the last one. So our matrix A here, let us come here and see, oh, I guess we can just do brackets here. And yeah, there we go. and we want to do, in this case, a 3 by 2. So there we'll have 6. Did that wrong there. So -6, and then 9, and then 9, 3, -9, and 3. Oh, let's see, what did we type in wrong? Well, let's check everything again. So, oh yeah, I typed in the wrong matrix. Yeah, so we need to actually type in this one. So I was just copying the wrong thing there. So let's just try again. So 3 by 2, and that needs to be 0, 15, 8, 7, -2, and 11. So we still got something going on here. So let's check. 6 plus -6 is 0. 6 plus 9 is 15. -1 plus 9 is 8. 4 plus 3 is 7. And 7 plus -9 is -2. And 8 plus 3 is 11. So let's see. That looks right to me. Don't know why it's saying that. So we'll just kind of figure out what it's saying here. Maybe we copied down the matrices wrong. So yes, and that's why. So here our A, that should have been a -4, not a 4. So I am sorry about that. Okay, let's make sure we have everything else right too, because that's going to affect some of our other matrices. So let me go ahead and fix this and get this to where it needs to be. So let's look here. I'll just pause it for a second and fix everything, and then we'll go ahead and type them in. All right, so I think I got everything fixed now because of me copying that one number down that wasn't correct. So you see that my matrix for A plus B matches the system here. So now we're going to go ahead and type in what A minus B is. And of course, this is also going to be a 3 by 2. And we'll type in 12, -3, -10, -7, 16, and 5. Of course, now 5 times A, go ahead and type in. So that's going to be 30, 30, -5, -20, 35, and 40. Okay. So last thing we need to do now is the 7A plus 6B. So I'm going to erase most of this and just leave the A and the B, and then go ahead and form that matrix there. All right, so now we have 7A plus 6B, and we've written in everything. So now all we need to do is come and figure out what everything's going to be. So for our first matrix here, we're going to have a matrix where that's 42, 42, because 7 times 6 is 42. And then in the next row we have -7, and then -28. And in the next row we have 49 and 56. And of course, we'll add to that 6 times whatever's in here. So that'll be a -36 there, +54 in the next slot. And then go to row 2, we have 54, 18, -54, and then 18. And so now from here, we just go ahead and add together. So if we take 42 plus a negative 36, that's going to give us 6. And 42 plus 54 there should be 96. Negative 7 plus 54, that should give us a positive 47. And a negative 28 plus 18 going to give us a positive 10. 49 plus a negative 54 is like 49 minus 54, which that should give us a negative 5. And 56 plus 18 should give us a positive 74. And so this should be the final matrix that we type in. Of course, this is 3 by 2 as well. And let's go ahead and type it. And let's see what we did wrong there. So that's 4 and 2, that's 6. 9, that's 6. Negative 7 and 54, that should be 47. Negative 28. 18, that should be a minus 10. And here, 49 and 54. That should be negative 5. And that should be 74. So, oh, yeah. I see what I did wrong. Got the minus 10 here. And I put minus 19 by accident. All right, cool. So we'll go ahead and conclude this video and pick up again on the next one to handle the next 3 problems that we want to do.